It looks like we can start. Welcome back, everyone. We're now on week 11, but welcome back for the break. I hope it was a restful one for you. With what we've got going on, quiz number 9 is the quiz that's kind of easy to miss rather, because this one's going to be due across from the break on Thursday of this week. And we're working through the Unit 5D on graphs in the media. Our last unit in Chapter 5 is going to be correlation and causation before we turn into skipping a couple chapters. We'll be into Chapter 8 after our Chapter 5 Unit E. But that's where we're at so far. And the other big announcement I have is that I have an unfortunate dental appointment on Wednesday that's going to lead to a class and office hour cancellation. So sorry for the cancellation on the middle of this week with us just getting back from the break. This one's going to be a root canal, so it won't be the funnest thing in the world. It's around 2 o'clock, but I feel like it might not be wise to hold class after an extended dental procedure like that one. But we'll still hold class on Thursday, office hours on Thursday as usual, probably working in Unit 5E. But any questions or comments at all, folks, before we get started today? Okay, well, again, welcome back from the break. We're on week number 11, which means we still have 6 weeks to go, counting this one, counting finals week. And with what we have going on in the further on schedule is a couple of ordinary weeks to get through, and then we'll have our third exam. So we'll be doing the whole thing all over again, where on Friday of this week here, week number 12, I'll be posting the exam 3 coverage, the sample exam questions, the formula sheet that'll be attached, and all the other information that you're expecting on exam 3. But really just doing the whole thing all over again that we did exactly in the same order, the same way for exams 1 and 2. Well, for the moment, we're going to jump back to example 2. Any last questions, comments, or thoughts? Okay, well, let's get started. We left here right before we were going on a really long break. So this was an interesting set of data. The context tells us that this is the per pupil public school spending for 17 apparently sort of randomly selected states, but this is mostly the eastern side of the USA using the 2025 data. So when we say per pupil public school spending, what we mean is the totality of all spending, whether it's for the school buildings, buses, the teachers, and so on. This is how much each one of these states are spending when we divide it among each of the pupils in the state. So California, for this data set, is right at the top. I think if we included New York, it'd be even higher than that. But no matter what sets we put in here, or states rather, even if it's all 50 states, the interesting thing is we happen to be in Idaho, which is dead last in the per pupil public school spending, which again, kind of an interesting side fact with Idaho there. Well, we mentioned that this graph is kind of deceptive in a certain way. We're going to explore that, but still answer some interesting questions about it. We're estimating the per pupil spending for Oregon and Idaho. This is an interesting comparison, mainly because Oregon is our neighbor. And just because the states are neighboring doesn't mean they're necessarily similar. They can be wildly different, as the status shows. Idaho is here dead last, and Oregon is over here on the upper end of the data set. Now, these problems are admittedly pretty tricky, especially when we're doing them in my lab, because we have to do a computation here as accurately as possible. So if you're having any trouble doing this in my lab, don't hesitate to ask about it. I'll be happy to help out, whether it's, say, an email, office hours, or even during class. If there's any of these graphs that you feel like you're struggling getting the values out to get through the question, don't hesitate to ask. We'll do our best we can on this one to estimate. And one thing I'd probably want to add to this graph before doing any kind of estimation is some horizontal dashed lines. The trouble is, it's not hard to estimate Idaho. It looks like it's somewhere around maybe $9,500 per pupil. Oregon's so far to the right that it's kind of harder to see just where it is. So let's add just a couple of horizontal lines, one at 1,500. And this is tough too. This is going to be a line that I'm hoping is perfectly horizontal, but it's hand drawn, so we'll do the best we can with that. If this was a quiz or an exam question and your numbers are in the right ballpark, I'm not going to expect perfect accuracy. It's understood that we're estimating this by hand or by visual on the graph. So here's the next horizontal line at $20,000 per pupil. Okay, not perfect, but it'll suit our purposes. So we're estimating the per pupil spending for both Oregon and Idaho. So let's start by saying for Oregon, the spending is going to be, well, let's see. The tick marks are kind of random here, going from 8,000 to 1,000, but then it seems to go by 5,000. So if we add a couple more tick marks, this would be at 16, 17, 18. That's not perfectly spaced, but that's 19,000 up to 20,000. And Oregon looks like it's tough to call, right? Somewhere between 19,000 and 20,000. So if we're estimating it and we give any one of those numbers in that around that range, again, we're going to be just fine. Let's say about $19,500 per pupil. So that's the estimated spending for Oregon. Then we just need to do it all over again for Idaho next. And again, these tick marks are kind of vague. This goes from 8,000. So we can say that that's about 9,000 up to 10,000. So our best visual estimate might be that that's about how, let's say, 8,500. So going with that, Idaho has spending at about 8,000. $500 per pupil. So double checking, well, hang on, that doesn't seem quite right. That tick mark right there was supposed to be 9,000, right? So just a little bit higher. That should be revised to 9,500. But again, if this was an exam question or a quiz question, I'm not going to be super picky. If you said somewhere below 8,000, somewhere above maybe 10,000 or close to it, we might lose a little bit of credit. But let's try to be a little bit more accurate for 9,500. I think those numbers look a little bit better. Any questions so far getting those two values for this part of the question? Okay, the second part of the question, we've done some of these problems before, way back in chapter 2. I think questions like this came up when we were looking into population densities, and we were wondering how much more dense a certain country is to say compared to USA, which is very low on the density scale. And it's the same kind of idea with this one. We're just wondering how many times more is the spending in Oregon versus Idaho. So when you see a problem like this, approximate ratio of spending in Oregon, really we're just looking at a fraction, and Oregon is what came first in this. So Oregon would be the numerator of that fraction. So we can say the ratio would be first for Oregon, 19,500 per pupil. So that's a ratio of spending in Oregon to spending in Idaho. The thing that came second is always going to be the denominator. So we're going to divide by our value here. It's an approximate because these values are estimates, or approximates in the first place. So 9,500 for Idaho. Hope that's per pupil rather. So here's the ratio that we get. Consulting the calculator, we've got 19,500 divided by 9,500. So I forgot to say what to round to on this question. Sorry for that distraction. I'd say 2 decimal places is about what you're going to see in the homework for these kind of questions. So this will be about 2.05. So what that tells us is, let's add this as an extra comment. Spending in Oregon per pupil is about 2.05 times the spending in Idaho. So again, that's not a pretty picture for Idaho, but that's what the information this graph is displaying. Any questions about that so far? Okay, again, this graph is kind of unusual in a certain way. It's a bar graph. Every one of these categories is a particular state. And we saw graphs kind of along these lines before. If we were, say, in the last unit, 5C, when we were to go and give a time plot, we put in the quantitative variable going this way, the year going this way. An equivalent comment from the class was, why not fit it to the actual data instead of starting at 0? If we start to around where the minimum value is, what you're really showing is the change in the CO2 levels on a decade by decade basis. It's not showing the absolute amount as much, but the showing the change was what we really want to emphasize in this kind of graph. But this graph is a little bit different because it's a bar graph. If we're trying to say, give this to people to paint a story for, say, the Idaho Senate, that we need to increase public school spending, we might be in trouble because this is not the world's most honest graph. Sometimes capturing the data like this is a good idea. Other times, even if this was an accident, it was probably not a good idea at all. This could harm us if we're trying to say increase public spending. And we're going to see exactly what's wrong in Part B. Part B is a slightly similar question, but it's focusing on the actual area of each one of these bars for the particular states. The area here is extremely small. Area here in Oregon is many times that for Idaho. And that's what this is asking us to address in terms of really just the lengths. It asks, what is the approximate ratio of the lengths of the bars for Oregon and Idaho in this graph? That's the main thing you would focus on if you saw a graph like this. We respond a lot better to the actual area that we see amongst the states versus the numerical data. That's the first takeaway we would have for the average person when they saw this graph. So part B is less about the actual numerical ratio spending and more just the visual impact on the graph itself. So this one's a tricky question as well to get through. When it says lengths for the bars, we have to estimate these. Now let's start with Oregon. Well, let's call this Oregon bar length. And a good way to do this is, notice it starts at 8,000. So if we want to find the length of the bar, any bar, we can just take the height of it, subtract 8,000, and that's going to be the length of any which bar we're looking at. So if we're interested in Oregon, we would use this estimate we have that the height of that bar is about 19,500. But the length, because it starts at 0 on this chart, would be this number minus 8,000. So take this number here, 19,500, subtract the minimum value in this chart, so minus 8,000, and we're going to get a length for this one coming out as 1,150, or excuse me, 11,500. I'll just say units, since we're focusing less on the dollar sign, mostly just on the actual length in terms of the scale here. So that's the length for the Oregon rectangle or bar, if we prefer. Doing the same for Idaho, we estimated this one at 9,500. So we'll subtract 8,000 on that, and that's the approximate length of the Idaho bar. So let's complete the next line here. Idaho bar length is 9,500 minus 8,000 once again. So we get 1,500 units on this one. And now we can find the approximate ratio, this time not of spending, that was 2.05, but of the lengths themselves. So let me see if I can zoom out just a touch here. So the ratio of lengths, again, the order is the same. It would be a confusing question if we switch the order. But we're going to start at Oregon, so the numerator is going to be 11,500 units. Whether you call it units or dollars, the unit is going to cancel out regardless. Divide by 1,500 units here. And so here's what the ratio comes out for on this one. 11,500 divided by 1,500 comes out to about 7.67. So then what that would tell us now is that you could say the area or the length. I want to focus on the area for this description because the principle here is sometimes often called the area principle for these kinds of graphs. The area of the Oregon bar is 7.67 times the area of the Idaho bar. So that's pretty stark, and we can kind of see that here. Idaho seems really minuscule. When we see that and have a gut reaction to it, the first thing we're thinking is Idaho is spending almost nothing per pupil, and Oregon is spending many times it. I might have, if I was just visually estimating, without doing this step right here, I might have said Oregon is about 10 times the spending in Idaho, but that's not quite the story. The spending is 2.05 times. So these figures are way, way off. Well, any questions at all, folks, with those two computations there? Okay, really what's kind of going on in this unit is this is about graphs in the media as the unit title. Many of the graphs that we're going to look into the reading and in the homework are honest, very informative graphs, but some of the discussion you'll see in the reading are about graphs that are a little bit less honest, and this is our first one that we've seen in the set. I think it's actually the only one that you'll see in the homework and in the notes. Even though the data is real, the graphs themselves need to be presented better as a bar graph. And it says now in part C, based on your answers in parts A and B, do you consider the graphs to be deceptive? Well, any volunteers for a quick response on that one? I'm noticing also that I kind of gave away the story on part C as we went through this problem and even introduced it. One quick way to answer this kind of question is you could just say yes to them being deceptive because the bar chart does not start at 0 on the horizontal axis visually. Spending in Idaho appears to be vastly less than it actually is. And even though this could have been well meant when people construct this graph, they weren't trying to be deceptive necessarily and just made that design choice. The trouble is, if you're trying to present this data in this way, the critics, the people trying to counter your argument, can focus on this design choice, say that you're being deceptive, and just completely sideline your argument, which would be really unfortunate because, again, this is important data. This is important things to think about. You wouldn't want to have any kind of distraction in your message, like the fact that your graph might be deceptive. Well, that's our second graph. Again, I don't have a lot of graphs like these that are meant to be intentionally deceptive. I think the last example is kind of along these lines in a certain way, but we'll see what goes wrong with it when we get to that last example. But any last questions or thoughts, folks, completing this example here?
I have a question. My first thought on that when I looked at C and I started thinking about it was the fact that the graph shows that it's 2.05 instead of the length which shows it 7.67. If I had just put that in there and didn't reference that that the bar graph started at 8,000 instead of 0, would that still be considered correct, or do I need to make sure I'm referencing the bar graph starting at 8,000?
Gotcha. Yeah, I would say your answer would be terrific. Really, two good answers are I focused on the bar graph not starting at 0, but your answer in a certain sense is a lot more informative because the fact it does not start at 0 means the ratio for actual spending, real spending, versus the ratio for areas are way, way off. So if you focus on that aspect completely alone, I would say that that'd be a great way to answer this question for full credit as well.
Okay, thank you.
You bet. And let's actually add that on just as another sentence. Let's say since, well, maybe let's keep this as a discrete thought. We could loop it in by saying since it does not include 0, these are way off. But another great way to answer this question is just as you said, because real spending between, let's say, the real spending ratio, to be specific, because we were talking about the ratios on both of them, because real spending ratio between Oregon and Idaho is 2.05, and the area ratios or ratio is 7.67. That alone, just like you said, makes this a deceptive graph. So let's say here, the graph is deceptive. So either way you'd like to take or answer this kind of question, I would say would be very appropriate. Other questions or thoughts on getting through this problem? Okay, so far our graphs have been pretty interesting. This one's a standard bar graph, but graphs can get really convoluted like this one. We're comparing geographical data with categories for numerical looking data as well at the same time. So this is a pretty interesting graph. And it can get pretty wildly interesting beyond that. This one has a lot going on just on its own. Here we have another bar chart, but notice that there's kind of a magnitude direction. Some things are positive, some, well, one value is negative. This expands on it where directionality is important, positive and negative, but it also has more data. We have the categorical data of splitting up values for 2000 and a 2040 projected values. And then it gets even more complicated if we say take bar graphs like these, look at two variables side by side that have different units, different scales, and compared across years. The idea with the last three examples is just to try to absorb what the graphs are even saying as they slightly get more and more complicated. Trying to read these graphs is, again, a pretty decent skill in and of itself. So we'll take our time with each one of these. Starting with the percent change in CPI between years 2004 and 2025 rather. Let me scroll down just a bit. So here's a pretty interesting bar graph going from 2004 all the way up to 2025. On our vertical axis, we're looking at the percent change from previous year. And if you think about that, those are computations we looked at before. If you're looking at percent change from previous year, these are essentially inflation numbers. In fact, that's how we calculate inflation. We looked into a formula that went about like this. If I can get the right tab, let me go down. Sorry, I thought I had the right spot there. When we looked into finding the inflation values, we took 1 year compared against another year, we divide by that year, multiply by 100 to turn it into a percentage. The only thing that's different from here is we're going from 2004 to 2005, we would have CPI 2005 here, CPI 2004 here, and here. So this is just from 1 year to the next. So not going across from 2025 to say all the way back in 2005. That one was a 64.8% change in inflation, adding up all these numbers across the top. In fact, this table right here, or this chart right here, is based off our same good old CPI indexes here. This gave us the approximate cost of various goods and services on a year-by-year basis, where the years 1982 to 1984 are the base years. If we look at, say, 2025 being 321.9, what that's saying right there, that cell is prices and services were on average 321.9% what they were in these base years here. So this table is, this bar chart rather, is completely just based off this table here. And there's other weird things that happen. Notice that there's one negative value. So this bar goes down below. We now have more dimensionality to our bar charts if we allow that to happen to convey that negative value. This was in 2009, during the year of the global financial crisis, the housing bubble. And if you look at 2009, it was the prior year a little bit more, and then it actually went down. I think that's the only time it goes down in this entire table. I'd have to check some of the earlier decades here to know for sure. But really stands out here when we see it as this kind of display, looking in inflations themselves. So that's the story of what's going on with this chart. Any questions about it so far? Okay. Again, the thing that's new about this is it's a bar chart just like on the prior example, but one new thing is we have a negative directionality that is possible for this kind of display. And also the values here are percents this time. So that's the next major thing that we're gonna have to think about when we analyze the information in this graph. Starts off by saying, based on this graph, in which specific year was the percentage change in the CPI the greatest? And that was not too bad. We're looking for the greatest percentage change in the CPI. We're just looking at the highest value. This description right here matches up just fine with this description. So these are very compatible questions. We go to the highest chart, or excuse me, the highest bar on this chart. This is year 2022, right after COVID was really getting going. And I think we started printing a lot of money and inflation jumped. It's at 8%. So 2020 year had the greatest change in CPI. Let's write here. In 2022, the percent change in the consumer price index, CPI for short, was the greatest. So this question part A is nice because once again, the statement of the question aligns just nicely with the actual information on the vertical axis. Any question with part A? Okay, here's the one that's a little bit weird now. Part B is nothing like part A in a certain sense. The problem is we're being asked in which year was the actual CPI value the highest. But when we say actual CPI value, that's in a direct conflict with this vertical axis. So we have to be cautious. Let's put here for a quick note. This is a different variable than the y-axis variable. Let's pause and think about this one for a moment. Any volunteers for the assessment on which year had the highest actual CPI value? You're close. It's not quite 2022, but you're on the right track. CPI 2004, well, let me start this way. CPI 2005 went up because the percent change was 3.4%. So it actually went up. The CPI in 2006, it went up as well, not by as much, but because the change was 3.2%, that's how much it grew by. It went up again in 2007, but not by too much. 2008, it really jumped by nearly 4%. But then in 2009, CPI went down, which is kind of shocking. Again, that had a lot to do with what was going on globally, financially. But then it went up again in 2010 and so on. And so again, that's what makes this question really kind of tricky. It went up a lot in 2022, but amongst all the years, which year would you say it was at its very highest value? Turns out it wasn't 2021. And yeah, I agree with what Amy's saying. It's kind of hard to figure that because these are percents and it's giving percent change from the previous year. Yet the question is CPI. We don't have a graph for CPI that we're looking at whatsoever. So there's got to be another way to kind of figure this. And here's the thought that goes along with it. I'm going to cheat a little bit just for the sake of putting the two thoughts together. If we happen to, and again, this wouldn't work on a different kind of context, but if we were to happen to look at our CPI number, we can see that it's going from 20, and let's see, it starts at 2004 here. So in 2004, it starts at 1899. It starts going up and up and up, except for 2009. It dropped down a little bit. But all these are positive percent changes, meaning it keeps on going up. Even in 2015, it went up by a little bit, 236.7 to 237. Not much, but that was an increase, even though the value was very, very close to zero. But notice if the question is which year was CPI the highest, it's absolutely 2025. The reason being is all of these are positive percent changes, meaning the CPI numbers just keep on going up and up and up as the years increase over and over again. If one of these was negative, however, it would have gone down in that particular year. If it went down by a lot, this would have been a hard question to answer, but it only ever went down once. And so we can see from the chart, the values just keep on increasing no matter how large or small the increase was. All of these are CPIs getting higher and higher, and it caps out here, 2025. I bet if we add 2026 with the next year's data all rolled in, it's just going to be higher as well. It'll be interesting to see what the inflation number is. And that's our number we see here. Again, this chart, we are imagining we didn't really have it. We're just seeing how the percent increases are showing the increases in CPI. So it turns out that year with the highest CPI value was 2025 altogether. Let's put to words what the explanation was so we can have something official to think about. But any questions about that so far? Thinking about that highest value here? Okay, let's put this down and then really focus on the explanation because once again, part A is the nice question because it lines up with the axis. But because it's a percent change question, part B is a very, very tricky question just out of nowhere. So we can say here altogether, the year with the highest CPI, oh, that's going to be because of all the positive values that we see here. So let's loop that into the explanation as well. When we see all these positive values, that means the CPI wasn't just at its highest in 2022, it grew here and it grew here, and then it grew in 2025. So all these values, because they're positive, I could circle all of them until I get to negative 0.4, but let's focus on these big ones. All of these are showing CPI growing on every single one of those years. So we can say altogether, the year 2025 has the highest CPI. So that's the answer, but let's be really careful with the explanation. This is because let's focus on this axis unit right here. The percent change from the previous year. That deserves a color at this point. The percent change in the previous year and there is one exception, but again, that's less than 1%. So it only went down just a little bit, and then it's up and up and up in all these other years. But let's make sure we're very, very careful we write this out. Percent change in the previous year is always positive, except way back in 2009. This means CPI grows every year until we reach the last year of 2025. So that's one way to think about it. Let's add a little bit more to the explanation visually before we end on this one, but any questions so far with the explanation here? Okay, let's change the charts just a little bit. Let's suppose 2025 went completely differently, kind of like 2009. If in 2025, we actually had something that looked like this, and that's pretty extreme. Let's say it went from negative 3.8% or something like that in that year, 2025. Let me see if I can white out this part. Let's just maybe black it out. That'll do. So let's suppose 2025 was a different sort of year, really. And for some reason, we had deflation. CPI went down a whole bunch. We know that's not the case because prices everywhere seem to have gone up. They haven't gone down. But if this was the real chart, maybe in a different country, the answer wouldn't have been 2025. It would have been 2024. The reason being is It's going up from 2024 to 2025. That's one off year in 2020, 2009. Sorry, I'm saying those years weird. It's positive in all these years. CPI only goes down once in this year right here. But these percentages being all positive means CPI keeps on increasing every single year after year. But that's the last year of increase. So the values just kept going up until 2024. That would have made it the highest value in the CPI index. And then here, if it had a negative 3.8 decrease, that stays the maximum value in the data. So that's how the problem would change if we change the graph like this. If we change it even more, say, we'll hack out this year and say 2024 was just as weird. Prices went down maybe 1.9%. Well, these don't have percent symbols. The percent's on the vertical axis. Then it would have been 2023 that had the highest CPI value. Does that make sense with those just additional ways to look at different graphs here? Okay, definitely so far, this is one of the trickier graphs, right? It's not just about how some values can be positive and negative, the real graph having just the one negative value. It's also the fact that this is about percent change makes this a really particularly confusing graph to think about. So I appreciate all the questions so far. Any other questions at the moment before we take a look into the next?
Just a quick question. So I just
Yeah.
want to make sure I understand this properly. So let's just say it asked us what year had it was the lowest, right?
Yeah.
Then we would look at probably 2004 where we started because it had so many increases in it.
Yeah, exactly. There's
Okay.
one decrease, but it's really, really small. So it wouldn't really factor in a whole lot. In fact, that's a really good question. I kind of wish I asked that on the notes. Let's say that this is B part 2. In which year was the actual CPI value the lowest? Explain. The explanation is pretty much the same as before, but let's add this in anyways. And just like you said, 2004 has a CPI value in particular. It didn't tell us what it is based on this chart. But if we are starting at 2004, the very next year it's higher because the percent change is positive. It moved up. It moved up more, it had even more. And then it was almost neutral, just barely edges down. But then with all of these positive, CPI just keeps on going up and up and up. So for this additional question, as you posed, we would say the year 2004 has the lowest CPI. And let's add just a faster explanation. And we can say this is because the percent change is always positive. Let's qualify it because there's one exceptional year close to zero, but it was negative, except for 2009. If the percent change is always positive, that means every single one of these years guaranteed has a higher CPI value than 2004. Even in 2009, let's check the actual data. Again, we wouldn't be able to do this in, say, a homework or a quiz potential exam problem. So this is just our way to tie the concepts together. So if we look at 2004, here it is, 1889. Then it goes up, 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 up. It went down, but the amount it went down is very, very small. So that value in 2009, 214.5, is still quite a bit larger than the 2004 value at 118.9. And then looking at all these other years, it just keeps on going up. In some years, it looks like it's in fact accelerating around this range. It's going up quite fast at this point. Well, other questions about that so far?
I have one more question. Will we
Yeah, go ahead.
ever be faced with a graph where there's a lot of positive and negative changes where we would have to like add and subtract the percentage of change to figure that out? Like, will that be something we'll have to calculate for the class?
I would say no, because yeah, that one would get pretty messy and involved.
Good,
But
just
for what
making
you
sure.
said, it could be done. You could add them up and start making those comparisons. So it could work. But I would say this is about as dicey as it's going to get on this one.
Okay, good. Thank you.
You bet. Thanks for asking about that. Yeah, I can imagine if there was just like kind of randomly up and below, now it becomes kind of a really hectic problem to answer those questions. Other questions so far? Okay, I think we're nearly done with this problem. There's a couple more to take a look into. And let me pull the chart down just so that we can not have to scroll up and down as we look into these last questions. Don't know where that came from. Let me try again. Okay, that's the actual chart. So part C is now asking, in your own words, explain what happened to the actual price of goods and services in the year 2009 compared to year 2008. So part C is now looking like it's all about seeing what's happening in this range. Really emphasizing the directionality of the graph, the fact that we have a negative altogether. So this one, I don't think is as tricky as the others that we were just looking into. Here we can say in 2009, the percent change from the previous year was negative. But then we have to say, what does that mean? If the percent change is negative, that means the CPI itself would have gone down. And that's essentially all we really would need to say. The percents are from one year to the very next. So we can say what happened in year 2009 is in 2009, the CPI went down by 0.4% from 2008. I wrote it as a positive value here because when I said went down, that already conveys the negative sign once already. If you said went down and you put a negative here, it's technically double negation, but I wouldn't be super picky about that. Typically, this is how it'd be more likely written. So if 2009, the CPA went down by that percentage, this means the CPI in 2009 is smaller than the CPI in 2008 altogether. And again, this is one of those rare times where we can double check that. In 2009, CPI is 214.5, and it's in fact smaller than the CPI in 2008, 215.3. So that CPI is in fact just a little bit smaller, not by a whole lot. So now we can explain what happens to the actual price of goods and services in the US by just saying if the CPI is smaller, that just means the price for those goods and services are lower on average. So we can say this means prices on average were lower in 2009 versus 2008. Again, in my lifetime, I think this is the only time that's ever happened. So it's kind of strange to see this. But I'd have to double check these other years to really make sure that's in fact true. It looks like it's in fact always going up. I don't think there's any other exceptions if we put in this entire table into this graph. But any questions, folks, looking into that particular targeted years, 2008, 2009? Okay, well, we're nearly done with this table, so let's take a look at the final question on the set. It says next, consider the period between years 2010, 2020. So now we're in this range. Capping it off at 2020 for no apparent reason. So in those years specifically, it says next, even though some of the bars are shorter than others during this time frame, we can verify that this bar is really close to zero. None of them are negative. Some are pretty tall. 2011 was particularly large. So it kind of goes up and down a little bit, kind of a wave pattern almost. So even though some of the bars are shorter than others during this time frame, the actual CPI values continue to rise every single year. And that'd be true even if we went up to 2025. So this question might feel kind of redundant, but it's a good one to take another separate look into. Explain why this is true based on the data shown. The actual CPI values were rising every single year. Well, it goes back to the way we're kind of analyzing this chart, much like what we were saying in 2009 versus 2008. That year was weird when we went to 2009. That one-time CPI went down by 0.4% meant the CPI itself decreased. But if we look into here, the actual CPI values continue to rise every year is reflected in the fact that there's not one single bar that's negative in this region, this entire range rather. So all positive bars mean it's rising every single year. If there was one bar that looked like this, say 2015 was just a little bit different, that would have been a weird year. And then this would have been a lie. It didn't raise every single year in that range. 2015, it would have decreased by quite a lot based on the bar length. So again, addressing this question, even though it's kind of similar to our part B question, it's just another take on what's going on this table. We can say CPI is going up every year because the going back to this variable, percent change from the previous year is always positive. So it's, again, kind of a weird way to look into this graph. We typically, when we see these kind of graphs and we see a bar at this height and see it going down, we might feel like the CPI is going down. It's extremely counterintuitive, right? But because it's percent change, this is what makes this graph feel so different from all the others. Even when the bar is going down, because it's positive, CPI still went up. It just didn't go up by as much in 2012 as it did in 2011. So this is how much it increased by, is what the bar is telling us. And it's an increase in every single one of these years. It's a different way to say it. Where this year was very close to zero, no change whatsoever. Well, any last questions or thoughts, folks, thinking about this new take on CPI? Okay, the next graph we're going to take a look into has some similar features where values on the bars for the bar chart can be positive or they can be negative. It's going to be a little bit more tricky in the sense that we're looking into two different kinds of years at the same time, but the horizontal axis is different kind of categories, countries. But, I kind of feel like this chart might have been trickier. The next one is not about percent change. So the next chart is a little bit more straightforward in that kind of sense. So watch out for any problem in MATLAB that has a percent change. In my opinion, especially thinking about going through this problem, these are the trickier kind of graphs to think about. So here's the next one we're going to take a look into. We're looking into real world data for this. And this one is about net energy trade. So pretty complicated kind of unit. Let's get through the context carefully on this one. Net energy trade is the difference between the total energy a country produces and the amount its citizens and industries consume. So it's going to be essentially what the power bill is for every single country. Either they're going to be in the positive or they're going to be the negative, and the net energy trade is going to tell us where they're at. So here's our net energy, and it's in an interesting unit called quads. So our net energy trade is measured in quadrillion BTUs, BTU being the unit of energy and quadrillion being quite a large number. So we'll just abbreviate that to quads when we think about the energy on this now global scale for different nations. A positive value means the country is a net exporter. That means they are producing more energy that their actual citizens and industries actually use. They have extra energy, and since they have extra energy, they sell it to the world, various other nations. So positive means they're net exporter. And let's maybe highlight this to keep the directionalities together. The positive green will do the job. If it's negative, meaning the bar is below this horizontal axis we see here, negative means it's a net importer. It means together with its citizens and the industries in that country, they're using way more power than they actually produce as a country. If that's the case, they keep the lights on by buying energy, importing it from others. So it's a net importer in this case. So let's think about these two directionalities. Maybe blue is not a good color because blue is already in the graph. That would be kind of tricky if you threw that on there. Let's use negative as purple. Let me know if these colors are kind of hard to read on your screen if we highlight this way. I just am avoiding the colors of blue and orange already being important for the years 2000 versus 2040 projected. So the figure below shows the net energy balance for 4 major global powers. So we're not going to look into every country. This would be a really busy graph. So 4 countries, kind of randomly chosen here, but they're major global powers in year 2000. So that's our historical data. And although no one knows what's going to happen in 2040, people make projections, and we're projecting into 2040. So if everything is happening the same way as the country is going, if all their expectations work out, we're projecting it what their net energy will be in quads all the way into 2040 in this graph. So that's what the colors are mentioning here. Blue is historical, orange is the projected data, and the categories go Norway, China, US, Japan. The vertical axis is also net energy, which can be positive, capping out at 20, although this is a little bit shy of 20, and all the way down to a negative, capping out at negative 40, although China seems to be right around negative 30 in this graph. Lots going on with this one. This feels like it has really 3 kinds of dimensions. It has the net energy, it has the country, and then it has the year, historical versus projected, all together. Well, any questions about the graph so far as we're kind of eyeballing it, digesting what it says visually? Okay, well, now that we've taken the time to think about this graph, again, it's pretty tricky, but I have a feeling the example 3 is a little bit worse because this one's not a percent change graph. This is just the net energy. It would have been as if we're looking at CPI, not percent change in CPI as a graph. So it asks us in year 2000, meaning all we care about is the blue graphs, the blue bars in the graph rather. In the year 2000, which of these countries were energy dependent, meaning they had to import energy from other nations? Any volunteers for which energy dependent nations there we have in this chart?
China, the US, and Japan.
Yeah, absolutely. And it's kind of a jump through hoops you have to do, right? When it says which one are energy dependent, means we're importing the energy. Importing means negative value on the net energy quads, but only in year 2000. So just like you said, that was China, US, and Japan, because all the blue bars below the horizontal axis. So good eye on that one. Let's put down here, China, US, Japan. It didn't ask us to explain, so let's put this as just an additional comment. It says 3 since all blue bars because they're talking specifically year 2000 are below the horizontal axis. So lots of energy dependent countries in this chart. Follow-up question says in part B, still year 2000, so we're still just thinking about the blue bars in this chart, none of the other bars whatsoever. Which of these nations were net exporters of energy? Once again, it's kind of a definition loop or set of loops you have to jump through. Net exporters, let's think about what that meant. A positive value means it's producing more energy than it's actually using. So it sells it, or in other words, exports it. But that would just mean the bar is above the horizontal axis. The only blue bar to target year 2000 above the horizontal axis is Norway. So part A is kind of the opposite of part B altogether. We'll say here, just Norway, since this blue bar is below the horizontal axis. So far so good. Any questions at the moment, folks? Getting through these two questions? Okay, now here's where it gets a little bit tricky because now we have to estimate. Part C is asking, which country is projected? Let's pause right here. The moment they say is projected, that means we're using the orange bars, the 2040 projection. I think that's a good comment to just make right away. Use orange bars, now that it's talking about the projections. Which country is projected to undergo the most significant change? Well, let's think about that. Norway undergoes a change because it goes from what looks like about 9 quads to maybe 8.5 or 8 quads. It decreases. And China is a pretty interesting country. It was almost net energy neutral in the year 2000. Their industry went kind of ballistic and really has kicked up and is projected to drop by this change, a negative absolute change. And USA is pretty interesting. We're gone from highly energy dependent, way more than China by a lot in the year 2000, to, I think this is the advent of different kinds of oil refineries that can deal with sandy shale oil, to fracking, to all sorts of things that have happened over the years since 2000. We're projected to be an exporter of energy. Japan has just been energy dependent, but they're improving. That's a small change. So to answer this question, it's really between China and US. Notice that this is, well, I said use orange bars when I said is projected, but I think that comment is probably not the best. We have to use both the orange bars and the blue bars at the same time. So let's maybe add to that, use orange bars and blue bars. Well, any volunteers for which one appears to have the most significant change?
That would be the US.
Yeah, I agree. To be honest, it actually is kind of hard on my eyes to see the absolute difference between the two. These, to find the difference, I would have to take for China. I need an estimate, and they're at, say, about negative 28 quads. Then we minus in the 2020, that's about negative 2 quads. So their change is negative 26 quads. Now, if we do the US, this is the right one. But again, to my eyes, it's kind of hard to see. Maybe if I focused on the orange bar and the blue bar, the fact that this orange bar is way bigger than that blue bar, but for some reason, for me, it's easier to just kind of estimate. If I take the projected value for USA, which is maybe about 12 or 13, let's go with 12, minus the value here for 2020, which was pretty low at maybe negative 22. Notice that this number is quite a bit bigger in magnitude. We're not looking at which one is more positive or more negative. We're just saying which one has changed the most. China has gone down by 26 quads. USA has gone up by 34 quads based on this calculator estimate. So this one has the biggest change altogether. So we can say here, US has the largest change. We went from, in the year 2022, we have projected 2040 to, let's say, minus the year 2000 value. We found that that's, through the quick calculator check, approximately 34, which is quite a lot larger than China altogether. So that means US has the largest change. China is the runner-up altogether. But again, anything can happen in this thing. If we do this whole problem all over again in 10 years, the projections are almost surely different for 2040 or 2050 if we're still going for the same kind of gap. And this is going to look like probably a lot different kind of table altogether. So any questions at all, folks, getting through the part C on this one? Okay, there's one more follow-up question to take a look into on this graph here. I think it'll be probably a good idea to not rush through the last one. The last one is asking which country is projected to have the most significant reversal of their net energy trade. That looks like it's going to be the USA as well, because no other country has a reversal. This is both exporting in year 2000, 2024, importing for China in both years, and same for Japan. But let's answer that carefully when we come back on our Thursday's class. Again, if you missed the announcement, I have a cancellation due to a unpleasant dental appointment on Wednesday. I'll send out an announcement Wednesday morning, just as a reminder as well. Then on Thursday, we'll finish this one off. Go to the last question on the Idaho potato industry trends, kind of riveting data there, and finish off this unit. But any last questions or thoughts, folks, before we call it a night? Okay, well, thanks again for the participation. Excellent questions and comments so far. I think these charts are definitely pretty confusing to get through. I think this one for me was the one that seemed like it was the worst because of the multiple dimensionalities of data, but there's one just like this as well in the homework. So watch out for this one. This will be a good notes to come back to when you're doing this related question in my lab. But have a great night, folks. We'll be back to it on Thursday. Thanks, I appreciate it.